Hi there, it's Dave Clelland from MBSI WAV, and welcome to another edition of Tech Talk with Dave. So today we're going to talk about some common and not so common knowledge items about Ethernet itself. So we're going to go through and Ethernet is kind of the heart of the data link layer is where it resides. And of course the data link layer is connected to the PHY, which is connected to the other device or other devices that it's speaking to. So let's take a little bit different view than what we did a couple of sessions ago. So the OSI model, Open Systems Interconnect, is what it stands for, describes the stages of communication. We've been over that. The application layer interfaces with the humans or other machines. The physical layer connects to another computer or device, and the layers in the middle interface with each other, forming the speech or the data used in the communication itself. Data is formatted. Data is never sent raw from one place to another. There's always it's encapsulated. There's the application layer, the data that we generate when we click our mouse or whatever, or type on our keyboard, is encapsulated by the presentation layer, the session layer, the transport layer, the network layer. And then finally it's delivered to the data link layer, and then of course to the physical layer and sent off to the other wherever it's meant to go to. The protocols used in each layer, common to us, may not be a layer of the OSI model itself, like some people believe that it is. So, for example, I've outlined on this particular slide, I've outlined some protocols in blue, some in green, and a number in red. The red tells us functions of the OSI model that we would associate with a lower level that really aren't. For example, DNS and DHCP are actually application layer processes. They're the end of the communication. So when a device comes online and it's looking for an IP address, the DHCP client in the device, when it senses that it's got a connection to the outside world, will take and look for the DHCP server. The server, when it hears the probe, will take and respond and transfer the IP address. That's a layer 7. People often associate that with the network layer of layer 4, but it's really not. It's really the layers are the applications that we commonly use every day are scattered throughout the layers of the OSI model. All right, so here we have the physical layer and the data link layer. And this is what we'll concentrate on here. 802.3, IEEE 802.3 is the Ethernet standard. It has both layer 1 and layer 2 membership. The IEEE 802.11 standard is Wi-Fi. It has the also physical layer, and it has data link layer membership, as do most of the protocols that are in here have membership in both layers. So the layer that we're concerned about here, the data link layer in this case, is the layer that has the machine or the device addressing. So when I have a switch like these routers that I have sitting on the table in front of me. Each one of these ports has a unique MAC address, or a machine, or a media access layer address. And this MAC address is the actual address that the system uses when it identifies itself to its connected partner, and the partner uses to identify itself to the other device that's connected to it. So this is a two-way layer. So a little bit different diagram here. Layer 7 through layer 4 formulate the data. Layer 3, once we've got an IP address, adds the IP address to it. Layer 2 formats the Ethernet frame type, adds VLAN, priority, source MAC devices. The source MAC ultimately will add the destination MAC address to it also after it has figured out what that actually is. Layer 1 converts the Ethernet frame into bits and or symbols, and transmits the media from this device, the device that originates the transmission, to the receiving device. All right, So how is this Ethernet frame constructed? This is a very important slide to understand because you can see here that the Ethernet layer itself is a data link layer function. The layer, the PHY itself is just a collection of, in this case, octets or bytes that are transmitted from one end to the other. So the layer 1 has size anywhere from 72 to 1530 octets. And there's an interpacket gap of 12 octets every single time. The two frames are never put right back to each other. There's always a gap. And so we have at least 12 octets are the gap. If since Ethernet is an asynchronous protocol, it could be much more than that. The gap could be much larger than that. But in a string of frames together, we have at least 12 octets that are dividing up each of the individual frames at layer 1 at the physical layer. In layer 2 now, what we have going on here is we have a destination MAC, a source MAC, and VLAN tagging, and other things that are going on, of which part of that is the payload. So the MAC, the data link layer, can range from 64 bytes to 1522 bytes or octets. Octets meaning 8 bits. And so the difference in size of an Ethernet frame depends on the payload itself. So you notice in here that there's no IP address, or there's no any of the addressing or any of the protocol that's higher up in the OSI model is simply included in the payload itself. Ethernet frames have a fixed structure. That data link layer, once it's formed up and once the information is known of the destination, the source MAC, VLAN for example, the Ethernet type, and the frame check sequence are once all that is known, then it's handed down to the layer 1 to be sent to the other device. All right, this is all pretty mundane stuff up to this moment. So the important thing to know is that the construct of the payload here, which is what's variable in all of this, we have content that's generated in the application layer. We have the content is formatted in the presentation layer. The session layer tells us what the protocol type is. And of course, there's a number of different types that are included in this. Then, once the session layer has done its job, the traffic is handed to the transport layer, in which case addressing and the transport type are generated, whether it's TCP or UDP or secure, the number of different protocols that are listed there, handed down to the network layer then at that point. And at the network layer, the IP version 4, IP version 6 addressing, ICMP, whether the ARP protocol, that kind of thing is used to determine where this frame needs to go. There needs to be a conversion to a MAC address at some point along the way, and so we have all of this that happens all the time when when two computers are communicating with each other. Encryption can occur at layers 3, 5, or 6 for the payload, and I've listed a number of encryption types, typical types that are used above layer 3. Layer 2 tunneling protocol occurs, of course, at layer 2, in which case the encryption is done there. A key is transmitted to the other end, again in an Ethernet format, and then the scrambled frame can be decoded at the other end. And TCP congestion control regulates the size of the payload. So the more reliable the link is, the larger the payload is allowed to be. The less reliable the link is, the smaller the payload is, because the system knows that the most time wasted is a retransmission. So if I send a very long frame and that very long frame is full of errors, I'm going to have to take and resend that frame. And so it's better from a system perspective to take and limit the size of the payload in order to take and provide a better guarantee that the data is going to arrive intact at the other end. So typically we see TCP congestion control regulates size of the payload anywhere from a few hundred bytes up to 1,000 or 1,200 or something like that, depending on how reliable the link actually is. Now, what makes a system layer 1, layer 2, or layer 3 based? Got some examples here. Layer 1 based system, it's the PHY communicating with the PHY. The physical interface is connected directly to layer 7 is what these systems typically do. An example, RS-232 or RS-485 serial data systems. There's no addressing. There isn't any information about either end transmitted to either end. It's just bits into the system and bits out of the system. SCADA typically is the application for that. Sometimes point-to-point microwave systems may not have any addressing either. The baseband might be modulated directly and transmitted right to the other end. The receiving end then takes and converts the RF over the air back to baseband again, and then it sends it off to whatever the next device is. Layer 2 based systems have an addressing based on a MAC address. The payload is transparent. And the system, we typically identify them as being VLAN aware because, of course, the VLAN tag is an important part of the Ethernet tag, which we saw before. Most broadband systems today are layer 2 based and have various options for the payload that is carried in that Ethernet frame. What makes the system layer 3 based is addressing based on OSI layer 3 model. So the layer, the IP version 4, IP version 6 address, for example, the traffic is layer 3, is tunnel based from a CPE to the controller, from a customer premise device back to the controller on the network. Examples of this are teragraph based systems. Example is CN WAV, which uses an E2E controller. The connection nodes, the distribution nodes, and the POP nodes are addressed in IP version 6. So the actual system is a layer 3 based system, but the traffic, the subscriber traffic that runs over the system can be layer 3 or can be layer 2 based. And when it's layer 2 based, we've taken and used GRE tunnels to take and go to run through the layer 3 addressing to make it transparent to the addressing. LTE systems, for example, are also layer 3 based. The CPE is addressed via a layer 3 packet data network connection, IP proxy from a serving gateway within the EPC to the CPE, and the traffic is contained within a tunnel. This is the earmark of layer 3 based systems is that generally traffic is tunneled, and the addressing is used to tell the device what the next device in the system is to pass the frame along to. So how do we identify this layer 1, layer 2, or layer 3 architecture? Layer 1 networks are generally hub based. A serial hub, like is shown in the top picture here, has a number of RS-232 ports. These ports are connected from a field device, let's say, to the hub itself. And so any data that shows up on port 1 is repeated out of port 2, 3, and 4, and so on. Again, typically SCADA systems, IoT systems in our homes may be layer 1 based, and so whatever the device says, all the devices that are connected on that network generally can see that data. Layer 2 networks are what we call switch based. That is, a typical Ethernet switch will take and learn the source addresses, source MAC addresses of the devices that are plugged into it. And so then when a frame comes in on a particular port that's addressed to a particular MAC address, then the switch forwards that data, that frame, to the port that it knows that the source address is on. So the devices can handle much higher capacity. They can do this MAC address filtering so that traffic from one port only goes to the port that that MAC address is learned on. Layer 3 networks, router based. So now these are IP addresses. So there'll be typically an IP address of the traffic coming in from, let's say, from the internet, and that'll get converted to another IP address to be sent out of the router itself. Whether this is a radio system or it's an individual router, the process is exactly the same. So what are the limitations of each architecture? In identifying the architecture, layer 1 architectures have no addressing. So there's generally no limitations on the content. There might be a limitation on the size of the data frame that goes across the link, but there's no ability to filter any kind of traffic whatsoever. Layer 2 traffic, now broadcast domains, can be very large. In the MAC addressing scheme, there's a MAC address that is used to identify the device itself. Then there's a MAC address that's used to identify the broadcast domain that it's in. Typically, it's addresses all Fs in hex of what you can see with this. And so when one device sends out a broadcast, it goes to every other device in the broadcast domain. And when the domains get to be really large, the layer 2 domains get to be really large, this broadcast traffic can constitute a considerable traffic volume. So that becomes one of the limitations. And we do not want layer 2 broadcast domains to be very large because we have to handle this noisy traffic. And it may or may not be desirable, and we have to take and do something with it. All right, so in a layer 3 network now, IP subnetting limits the devices that can communicate with each other. We can set configure the subnet to include more devices or fewer devices, depending on what we want to do with that traffic that is in our layer 3 network. So typically, layer 3 networks are the most concise networks because you can size them just exactly for the size that you need them to be. But IP planning is critical to proper network operations. So it's quite easy to take and misstep with an IP plan. Anyway, we're going to talk more about layer 2 in the broadcast domains and how we filter those to make them manageable in size in the next session that we have here. So as usual, any feedback or any comments, any new topic suggestions, please send an email to marketing@mbsiwave.com, and we'll be happy to receive your comments, and who knows, maybe your suggestion will be the next Tech Talk. Thanks very much.